Hello, welcome back to our conversation about improper integrals. Today we want to talk about the second way that an integral can be improper. These are the less obvious ones. The first ones that we looked at had an infinity in the limits of integration, and when that happens they kind of jump out at you. And the integrals that we're going to look at today, you're not going to see an infinity, so at a glance it's just going to look like a normal definite integral, but what we have to watch for are infinite discontinuities. So anytime we have a rational function that we're trying to integrate, one of the things we have to get in the habit now of doing is making sure there are no infinite discontinuities on the interval, either at one of the endpoints or somewhere on the interval. Okay? So if we do, then we have to treat it like an improper integral and use that limiting process that we talked about in the last video. So today I just want to talk about the three ways that these infinite discontinuities can show up. They can show up at the lower endpoint, the upper endpoint, or somewhere in the middle. Okay. So first case is, notice it says f of x is continuous on a to b, a is not included, b is. So in other words, we have a discontinuity here at a. So for example, in this graph right here where I have my infinite discontinuity, this would be a, right? And we're trying to integrate out here to b. Okay. So if I want to do the integral from a to b and get this area, I have a problem because I have an infinite discontinuity right here. Well, we're going to handle that the same way that we handled the infinity, right? We're just going to rewrite this. We're going to rewrite this integral. I'm going to take my a, where my infinite discontinuity was, and I'm going to replace it with a variable. I'm doing the same thing with that discontinuity spot that I did with infinity. Once I have it replaced with a variable, I'm just going to make my variable approach a. Now, here's the important part of this. Notice that this is a one-sided limit. That's important. You've got to have that there. Remember, if you don't put a little plus or a minus, you are saying that that limit is the same whether you approach from the left or you approach from the right. In this case, if a is my lower limit of integration, when I approach a, I'm approaching from this side. The approach from the left never comes into the picture here. Because I want the area between a and b, and a is my lower limit, I'm going to come from some c value in here, whatever I choose it to be, or it's not a choice, it's a variable, and I'm going to approach a, but I'm doing so from the positive side. Right? It's a right-hand limit, and that is important. So that's if I have my endpoint, or my infinite discontinuity at the lower limit of integration. Okay. Now, the same thing can happen, but your discontinuity is at the upper limit of integration. So in this case, I've got my infinite discontinuity here at b, and I want to integrate from a to b and get this area in here. I'm going to do the same exact thing I did before with the infinity, right? The b is the problem, right? That's the place where the discontinuity is. That's the troublemaker. That's the thing that's making it improper. So once again, we're just going to choose a variable in there, get rid of the thing that's causing us trouble. Oh, I'm having trouble with my... Okay. So notice again, a stayed because a is a perfectly fine value. The b is what's causing us trouble, right? So b got replaced with a variable. And now I'm just going to make that variable approach what I want b to be. But, this time I'm making c approach b. And notice again, one-sided limit. It's from the negative side. For me, really helps to draw a quick picture of these ones so that I know whether I'm coming from the left or coming from the right. For those of you who are better at picturing things, you might not need to draw a picture, but for me, a real quick sketch helps a lot with these. Okay, so the last but not least, these can come up where that infinite discontinuity is in the middle somewhere. So notice I have a function that's continuous from a to b with the exception of c. So that would be, in this case, like if a was here and b was here. Right? And this is the classic problem I've been talking about since we started doing integration. You can't integrate over a discontinuity. No, you cannot. You know what? You can approach it though. Right? So again, what we're going to do is we're going to break it right there, right? We're just going to break our integral. I'm going to go from a to c, and I'm going to have to approach c from the negative side, and then I'm going to go from c to b, and I'll have to push back and approach c from the positive side. We just break it into two doubly. We take a doubly improper integral, break it into two impropers. So let's get a picture of that. So again, I go from a to c, and I go from c to b. And then you can see here, I have a problem, right? When I go from a to c, this is an infinite discontinuity. So I'm going to have to put a dummy variable in there and approach it. On this side, I have a problem, right? But now at least I have a problem I can fix. All I have to do is rewrite this where I'm approaching this value. On this side, I will be approaching it from the left. In this integral, I'll be approaching it from the right. So it's the same exact thing we did with infinities. The only difference now is it's going to be some finite value that we have to replace with a variable and approach. And the reason we have to approach it is because it's an infinite discontinuity. You can't integrate to, from, or over an infinite discontinuity. You can't be involved in the integral at all. All right, let's do an example. Okay, so you can see what I mean here when I say these ones are a little bit more sneaky, right? When I glance at this, I don't look at that and go, ooh, improper integral. No, it's a little bit sneaky, right? So as soon as you notice that you have a rational function, the first thing that we want to do now, we have to train our brains when we see an integral. If it's rational, check where there's vertical asymptotes. Check where you're going to have infinite discontinuities. And in this case, we've got a problem at 1, right? So I have an infinite discontinuity at x equals 1. Okay. So that means that I need to break this. So I'm going to go from 0 to 1, because 1 is where my problem is, and then from 1 to 3. So I'm going to have two integrals. Right? My first integral is going to go from 0 to 1, and when I approach 1, I'll be doing it from the negative side. My next integral is going to go from 1 to 3. And when I approach 1 on that one, I'm going to be doing it from the positive side. So these are both going to get rewritten with limits. In this first one, I'm going to replace 1 with an a. So I'm going to go from 0 to a. And again, I'm going to approach 1 from the negative side, because you can see I'm coming from 0 to 1, so I'm approaching it from the negative side. Hi. And then on my other one, I'm going from 1 to 3. This time, I think I'll replace my 1 with a b. Again, I'm going from 1 to 3. I'm approaching from this side. So now I'm approaching from the positive side. Okay. So I've got my setup here, right? I took my integral that had an infinite discontinuity in it at 1, broke it into 2 chunks so that my infinite discontinuity now is at an endpoint. Once I have the infinite discontinuity at an endpoint, then I can use limits to approach those endpoints. Okay, that's key. So let's go off to the side and do this integral. We really only have to do the integral once, right? I'm going to use this space up here. So let's see here. I have the integral. I'm going to rewrite this as to the negative 2/3 because that makes it easy to think about, right? I've really got a cloud situation here, but the d cloud is just a 1, so it's no big deal. Right, so this integral is going to come out to, when I add 1 up here, to the 1/3 over 1/3. So this becomes 1/3 cube root of x minus 1. Right, that's my integral. So down here, I don't have to worry about doing the integral twice. I've got the answer right here. So my first one, just going to rewrite. I feel like this is so much writing. It's 1/3 cube root of x minus 1 evaluated from 0 to a. And then my second one is going to be that same thing, evaluated from, this should have been a b, oh, nobody told me, b to 3. Okay, so this is going to be 1/3 cube root a minus 1 minus 1/3 cube root of 0 minus 1 or negative 1. So that's going to be, the cube root of negative 1 is negative 1, right? So this is just going to be plus 1/3. Okay, so that's the first one. The other one, 1/3 cube root of 3 minus 1 minus 1/3 cube root of b minus 1. Okay. Whoops. Oh. So here, let's see, 3 minus 1 is 2, so this is 1/3 cube root of 2. And then when you approach, oh, I'll just write, you didn't do the limit in the other one yet either. B minus 1. Okay, so again, we are doing here one-sided limits, and it's a good thing. So I'm approaching A is approaching 1 from the negative side. In other words, I have numbers that are slightly less than 1, right? So 0.9, 0.99, 0.999. That's important because when I do this, these numbers are going to become, let's see, tiny and negative, right? Negative 0, if you will. Well, the cube root of negative 0 is still just a 0. Right? So you may be saying, well, that would have been true from the other side as well, and that's true, but it could matter. Remember, when it comes to things like infinities, right? Positive infinity, negative infinity. Also, you get functions where if you approach from the left and if you approach from the right, that's an issue. Okay, so this first part's going to come out to 1/3. Over here, I've got a 1/3 cube root of 2. Over here, when I put a 1 in, this is going to be a little bit bigger than 1, minus 1. So cube root of very, very tiny 0. So that whole thing is 0. So I end up with 1/3 plus 1/3 cube roots of 2. That's a very specific area under that curve between 0 and 1. Okay, so let's take a look at this graph. See what we're looking at here. Okay, so notice here, there's our infinite discontinuity. But you also notice that asymptote, they're kind of coming together really quickly, so that's probably why we have a finite area here, right? This isn't a very wide, what's the word I'm looking for? It's like a very steep peak. It's coming up very quickly. It's not coming out really wide and slowly. Right? So, and again, because of the nature of this function, squared, this is why whether I approach from the right or I approach from the left, it didn't matter. If this was a different kind of asymptote, if it was one of these, those would have been a big deal for us. Okay, so the functions area between here and here, we are saying, even though that goes up to infinity in the middle there, I still have a finite area here. And that is 1/3 plus 1/3 root 3, or cube root 2. These are a pain. Again, they're very, I feel like they're very tedious. Nothing really new. We know how to integrate. We know how to do limits. It's just a matter of putting it all together and kind of keeping track of what you're doing. So it is a lot of writing. And it's not these aren't my favorites. I don't think these are anybody's. Well, I don't know. Holler if they're your favorites. Okay. Here's another one. Again, masquerading is just an easy integral. One might be inclined to write, ln of x minus 2 evaluated from 1 to 2. But hopefully then you would notice very quickly that when you plugged in a 2, you get the natural log of 0, which is a problem. Hopefully you would notice that that's a problem, right? Because again, here, look, I have an infinite discontinuity at 2. This is an issue. The good news is it's at an endpoint. So I don't have to do the breaking thing like I did last time. I'm only going to have one limit to really worry about. So I'm going to take this and I'm going to rewrite it. I'm going to replace this 2 with a variable. So instead of going from 1 to 2, I'm going to go from 1 to, we'll call it a. And then I'm going to take the limit as a approaches 2. And I'm going from 1 to 2. So when I approach 2, it's going to be from the negative side. That's important. It's a one-sided limit. Okay, so like we said, we know the integral of 1 over x minus 2. It's the ln of x minus 2. So I have the limit of the ln of x minus 2 evaluated from 1 to a. So I need to wait a moment. Minus the ln of, let's see, 1 minus 2. Good thing we left our absolute values in there, eh? Don't forget them. They're important. Okay. So when I approach 2 from the negative side, let's see. When I approach 2 from the negative side here, I'm putting in numbers that are slightly smaller than 2, right? So numbers like 1.9, 1.99, 1.999. So this is approaching a very small number, right? A negative number. It's approaching a tiny negative, this right here. Okay. Good thing though I have this absolute value sign. So that means this is really approaching 0, right? And the thing is, what's happening to the natural log as you approach 0? I can't take the natural log of 0, but I can approach 0. If you know what the natural log graph looks like, and I know you do, when I approach from this way, that thing's going straight down the negative infinity. Okay, now, I guess I don't need this anymore. I'm evaluating my limit. So I have negative infinity. Then minus the natural log of the 1 minus 2, so negative 1, right, which turns to positive 1. So minus the natural log of 1, which we know is 0. So I've got negative infinity, minus 0, also coming out to negative infinity. So what we're saying here is this integral diverges. Okay, so once again, these really aren't that different than the ones with the infinities in them. I think they're just a little harder to catch. And again, one of the things that you just have to do with improper integrals is kind of just get used to putting all those things together. Practice them to make sure that you have a way to organize yourself so that you don't get lost in the problem. It helps to go off to the side, do the integral, and bring it back. There's just a lot going on with these problems. In any case, any questions that you have, go ahead and pop in the end of the video, and we will address the next time we see each other. Have a good day.